On the first day of July 2025, a routine scan of the night sky from a remote observatory in Chile captured something that would shake the foundations of astronomy. A faint smudge of light, moving against the backdrop of ancient stars near the galactic center, triggered an automated alert. Within hours, astronomers around the world dropped what they were doing. The numbers coming in from the trajectory calculations were impossible to ignore. This object was moving too fast. Way too fast. Nothing born in our solar system could achieve such velocity. For the third time in human history, we had caught a visitor from the stars. The object was designated 3I/Atlas, and from the moment of its discovery, everything about it seemed designed to test our understanding of the cosmos. The 3I in its name tells you immediately what makes it special. That letter I stands for Interstellar, and the number 3 indicates its place in a very exclusive club. Only 2 objects before it have ever been confirmed as travelers from beyond our sun's gravitational reach. And yet, 3I/Atlas was already proving itself to be unlike anything we had seen before. To appreciate what this discovery means, you need to understand how rare these moments are. Humanity has spent thousands of years watching the skies. We have cataloged countless comets, tracked millions of asteroids, mapped the movements of planets with exquisite precision. But until October 2017, not a single object had ever been positively identified as coming from another star system. The universe is vast beyond comprehension, and the distances between stars are so enormous that the idea of something simply drifting from one system to another seemed almost fantastical. Yet the laws of physics demanded that such objects must exist. Planetary systems are chaotic places, especially in their youth. Gravity can fling objects outward with enough velocity to escape their parent star entirely, sending them on lonely journeys through the void that can last billions of years. The first confirmation came with an object that would be named Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. It appeared without warning, was spotted only after it had already whipped around the sun, and departed so quickly that astronomers barely had time to study it. Oumuamua was strange in almost every conceivable way. Its shape was elongated, like a cosmic cigar or perhaps a pancake tumbling end over end through space. It showed no signs of the outgassing typical of comets. Yet it exhibited a subtle acceleration that couldn't be explained by gravity alone. Some serious scientists even entertained the possibility that it might be artificial, a piece of alien technology drifting through the galaxy. While that hypothesis remains highly speculative, and most astronomers favor natural explanations involving exotic ices, Oumuamua taught us an important lesson. Interstellar objects might not look or behave like anything in our solar system. 2 years later, in August 2019, amateur astronomer Gennady Borisov was testing a new telescope he had built himself at his observatory in Crimea when he noticed something unusual. The object he spotted would become known as 2I/Borisov, and it was reassuringly familiar. Unlike the enigmatic Oumuamua, Borisov looked exactly like a comet should look. It had a bright nucleus surrounded by a fuzzy coma of gas and dust. It sprouted a tail as it approached the sun. Chemical analysis revealed compositions similar to comets in our own Oort cloud. Borisov was proof that the building blocks of planetary systems across the galaxy share common ingredients. Water, carbon compounds, the raw materials of life as we know it. An interstellar comet was still extraordinary, but at least it behaved according to the rules we understood. Then came 3I/Atlas, the Asteroid Terrestrial Impact Last Alert System, known as ATLAS, operates a network of telescopes scattered around the globe. Their primary mission is planetary defense, scanning the skies for asteroids that might pose a threat to Earth. On that July night in Chile, the ATLAS telescope in Rio Hurtado was doing exactly what it was designed to do, sweeping the sky for moving objects. The software flagged a candidate, as it does thousands of times. But when astronomers looked at the trajectory data, they realized this was something special. The first clue was speed. When 3I/Atlas was discovered, it was already inside the orbit of Jupiter, screaming through our solar system at approximately 137,000 miles per hour. That's fast enough to travel from New York to Los Angeles in about a minute. As it fell deeper into the sun's gravitational well, that speed would increase even further, eventually reaching 153,000 miles per hour at its closest approach to the sun. These velocities alone were enough to rule out any origin within our solar system. Nothing that formed here could move that fast unless it had received some extraordinary gravitational boost, and no such encounter was evident in its orbital history. The second clue was the shape of its path. Orbits can be described mathematically by a number called eccentricity. Objects on circular orbits have an eccentricity of 0. Elliptical orbits, the kind followed by most planets and asteroids, have eccentricities between 0 and 1. Parabolic orbits, where an object has just barely enough energy to escape the sun, have an eccentricity of exactly 1. Anything above 1 describes a hyperbolic trajectory, a path that enters the solar system, swings around the sun, and departs forever. Oumuamua had an eccentricity of 1.2. Borisov registered 3.4. The value for 3I/Atlas was calculated at 6.139. This was the most extremely hyperbolic trajectory ever observed for any natural object in our solar system. Its path was so straight that the gravitational pull of the sun barely caused it to curve at all. 3I/Atlas was a cosmic bullet, punching through our neighborhood at an angle and velocity that left no doubt about its interstellar origin. But there was a third clue, one that emerged more slowly as observations accumulated. 3I/Atlas was displaying cometary activity. Unlike the mysteriously inert Oumuamua, this visitor was venting gas and dust into space, forming a coma that extended thousands of kilometers from its surface. Within days of its discovery, telescopes around the world confirmed the presence of a diffuse glow surrounding the object's nucleus. 3I/Atlas was not just passing through. It was putting on a show, revealing secrets about its composition with every molecule it released. The timing of this discovery was almost miraculous. Had 3I/Atlas arrived a few decades earlier, before the deployment of wide-field survey telescopes and space-based observatories, we might have missed it entirely, or we might have spotted it only as it departed, as happened with Oumuamua, giving us just weeks to scramble for observations. Instead, 3I/Atlas was caught on the way in, still a month from its closest approach to the sun. For the first time in history, astronomers had a chance to watch an interstellar comet wake up, to study its activity as solar heating transformed its frozen surface, to train an unprecedented arsenal of instruments on a messenger from another world. The global response was immediate and intense. Within hours of the initial report, astronomers were digging through archival data from other surveys, searching for pre-discovery observations that might extend the known trajectory further back in time. They found them. The Zwicky Transient Facility at Palomar Observatory in California had captured 3I/Atlas as early as June 14th, more than 2 weeks before the official discovery. Additional images were found in Atlas archives from other sites, going back even further. One amateur astronomer noted that the comet had been passing in front of the dense star fields of the galactic center, its light lost among millions of other points, which likely explained why it hadn't been noticed sooner. This extended data set allowed for more precise calculations of the comet's origin. Tracing its path backward through time, astronomers determined that 3I/Atlas had entered the solar system from the direction of the constellation Sagittarius, near the heart of the Milky Way. This was unusual. Both Oumuamua and Borisov had come from the general direction of the solar apex, the point in the sky toward which our sun is moving as it orbits the galactic center. Coming from that direction makes sense intuitively. Objects that happen to be drifting slowly through interstellar space are more likely to be swept up by a star that's moving toward them. 3I/Atlas, however, came from almost the opposite direction. It was moving outward from the galactic center, traveling on a path that suggested a very different history. Researchers began to analyze the comet's velocity components in three-dimensional galactic coordinates, breaking down its motion into movement toward or away from the galactic center, lateral motion around the galaxy, and vertical motion above or below the galactic plane. The numbers were telling. 3I/Atlas was moving upward through the galactic disk with considerable speed, far faster than most nearby stars. This implied that it followed a tilted orbit around the Milky Way, regularly plunging through the plane of the galaxy rather than staying close to it like our sun does. Such orbits are characteristic of older stellar populations, the thick disk, and even the halo stars that represent some of the most ancient structures in our galaxy. A team led by researchers at Harvard University attempted to estimate the comet's age based on these kinematic properties. Their analysis suggested that 3I/Atlas originated from a star system in the Milky Way's thick disk, a population of older, metal-poor stars that formed early in the galaxy's history. The estimated age was staggering. With 68% confidence, the team concluded that 3I/Atlas is between 7.6 and 14 billion years old. Even the most conservative interpretation suggests this comet predates our solar system by billions of years. It may have been drifting through the galaxy since before the sun even existed. Think about what that means. 4.5 billion years ago, a cloud of gas and dust collapsed under its own gravity to form our star and the disk of material that would eventually become the planets. Earth formed. Life emerged. Dinosaurs came and went. Humans evolved, developed technology, built telescopes. And all that time, this ancient wanderer was out there, crossing the vast, empty spaces between stars, carrying frozen evidence of conditions in a planetary system that formed when the universe itself was young. The implications for science were enormous, but the practical challenges were daunting. Interstellar objects move fast. They don't orbit the sun. They pass through and keep going. Once 3I/Atlas departed, it would never return. Every observation, every measurement, every spectrum had to be collected during this single fleeting encounter. And the comet's trajectory, while bringing it close enough to study, never brought it particularly close to Earth. At its nearest approach, scheduled for December 19th, 2025, 3I/Atlas would still be about 170 million miles away, more than 1.8 times the distance from Earth to the Sun. Close by interstellar standards, but still tantalizingly far for the kind of detailed study astronomers craved. The solution was to throw everything at the problem. Ground-based observatories on every continent pointed their mirrors toward 3I/Atlas. Space telescopes adjusted their schedules to capture this rare target. Even spacecraft designed for entirely different missions were pressed into service. Their cameras and instruments turned toward a comet that nobody had known existed just weeks before. The Hubble Space Telescope obtained its first images on July 21, 2025, when the comet was still 277 million miles from Earth. Hubble revealed a teardrop-shaped cocoon of dust escaping from the nucleus, the unmistakable signature of cometary activity. Because Hubble was tracking the moving comet, background stars appeared as streaked lines in the exposure, a stark visual reminder of the comet's velocity. Follow-up observations in August helped constrain the size of the nucleus. The latest estimates suggest a diameter between 440 meters and 5.6 kilometers. The uncertainty is frustrating but unavoidable. The nucleus is embedded in its own coma, its light mixed with the glow of escaping gas and dust, making precise measurements difficult. The James Webb Space Telescope, the most powerful observatory ever placed in orbit, made its first observations on August 6, 2025. Webb's infrared vision can see things that visible light telescopes cannot, and its near-infrared spectrograph instrument was designed to analyze the chemical composition of distant objects. What Webb found was remarkable. The comet's coma was dominated by carbon dioxide, an unexpected result. Most comets in our solar system are primarily water ice, with carbon dioxide present as a secondary component. But in 3I/Atlas, the ratio of carbon dioxide to water was among the highest ever measured in any comet, more than 7-to-1. This unusual chemistry might indicate that the comet formed in a specific region of its parent system, at a distance from its star where carbon dioxide ice could condense, but water ice was less abundant. Alternatively, it could mean that 3I/Atlas has been exposed to intense radiation during its billions of years of travel, altering the surface chemistry in ways we don't yet fully understand. Webb also detected water, carbon monoxide, carbonyl sulfide, water ice, and dust. The presence of water ice grains in the coma was particularly interesting. Unlike the nucleus itself, which is too cold to sublimate water at large distances from the sun, these ice grains have been lifted off the surface by the violent outgassing of more volatile substances like carbon dioxide and carbon monoxide. Once free of the nucleus, the ice grains drifted outward, slowly sublimating in the relatively warmer environment of the coma. This layered release mechanism helped explain the complex structure of the comet's activity. Ground-based spectroscopy added more details to the chemical inventory. The Very Large Telescope in Chile detected cyanide, a common cometary molecule, and atomic nickel vapor. The presence of nickel was not entirely surprising. It has been seen in other comets, including Borisov. But there was something strange. Usually, nickel and iron appear together in cometary spectra, because both metals have similar volatilities and are typically found in roughly equal abundances in cosmic material. Yet no iron was detected in 3I/Atlas. This unexplained absence added another line to the growing list of mysteries surrounding this visitor. As summer turned to autumn, 3I/Atlas continued its plunge toward the inner solar system. Its trajectory brought it closest to Mars on October 3rd, 2025, passing about 29 million kilometers from the red planet. This close approach opened an extraordinary opportunity. The European Space Agency had two operational spacecraft in Mars orbit, the ExoMars Trace Gas Orbiter and Mars Express. Both were designed to study Mars, but their cameras could be repurposed to observe a target in deep space. The question was whether instruments optimized for imaging the bright Martian surface a few hundred kilometers away could detect a faint comet 29 million kilometers distant. They could. ExoMars TGO's Cassis camera captured a series of images showing 3I/Atlas as a fuzzy white, moving against a background of stars. It wasn't much to look at, but the scientific value was immense. Observations from Mars provided a second vantage point, separated from Earth-based telescopes by tens of millions of kilometers. By combining data from both locations, astronomers could triangulate the comet's position with unprecedented accuracy. The improvement was dramatic. ESA announced that the Mars-based observations had improved the precision of the comet's predicted location by a factor of 10. This was the first time astrometric data from a spacecraft orbiting another planet had ever been officially submitted to help track a celestial object. It was a proof of concept with implications for future planetary defense scenarios. The comet reached perihelion, its closest approach to the Sun, on October 29, 2025. At that moment, it was just 1.36 astronomical units from the Sun between the orbits of Earth and Mars. Solar heating was at its maximum, driving the most intense outgassing of the entire passage. Unfortunately, this critical moment occurred while the comet was nearly aligned with the Sun as seen from Earth, making ground-based observation extremely difficult. The comet was hidden in the solar glare, invisible to most telescopes. But not all telescopes. Several space-based instruments are designed specifically to observe the environment around the Sun. The ESA and NASA Solar and Heliospheric Observatory, SOHO, detected 3I/Atlas passing through its field of view in late October. NASA's Punch mission, a constellation of small satellites studying the solar wind, captured images showing the comet's tail as a short elongation stretching away from the Sun. These observations during the critical perihelion period provided crucial data about how the comet behaved under maximum solar stress. Some observers had worried that 3I/Atlas might not survive perihelion. Comets are fragile objects, loosely held together by their own feeble gravity and internal cohesion. Solar heating can cause violent outgassing that literally tears them apart. Borisov experienced nuclear fragmentation after its perihelion passage, shedding debris in a series of outbursts. A smaller, less cohesive comet might disintegrate entirely. But 3I/Atlas emerged from perihelion apparently intact. The nucleus was still there, still active, still revealing secrets. November brought another observational opportunity. ESA's Jupiter Icy Moons Explorer, known as JUICE, was en route to the giant planet after launching in April 2023. Though JUICE was still far from Jupiter, its path happened to bring it relatively close to 3I/Atlas shortly after perihelion. The spacecraft devoted 5 of its scientific instruments to observing the comet, including high-resolution cameras, spectrometers operating at multiple wavelengths, and particle detectors. JUICE observed the comet just after its closest approach to the Sun, when activity would be at its highest. The preliminary results were tantalizing. A navigation camera image from November 2nd showed the comet surrounded by clear signs of activity, with hints of two distinct tails. One was the plasma tail, made of electrically charged gas blown directly away from the sun by the solar wind. The other was a dust tail, composed of heavier particles that lag behind the comet and curve along its orbit. The full scientific data from JUICE won't arrive on Earth until February 2026, delayed by the necessity of using a smaller antenna while the spacecraft shields itself from solar heating. But even the preliminary images confirmed that 3I/Atlas remained robustly active well past perihelion. NASA contributed to the observational campaign with an impressive array of assets. The Psyche spacecraft, on its way to a metal-rich asteroid of the same name, captured images of the comet in early September. The Lucy mission, headed for the Trojan asteroids, photographed it from 240 million miles away. The Stereo Solar Observatory tracked it for weeks. The Mars Reconnaissance Orbiter's high-rise camera, designed for ultra-high-resolution imaging of a Martian surface, was pointed at the comet during its closest approach to Mars. Even the Perseverance rover, busy searching for signs of ancient life in Jezero crater, contributed observations from the surface of Mars. This coordinated campaign, involving ground-based observatories and space-based instruments spanning from Earth orbit to the depths of the solar system, represented something unprecedented in the history of astronomy. Never before had so many instruments been trained on a single transient target. The data collected during these months will take years to fully analyze. Every spectrum, every image, every particle measurement contains information about conditions in a planetary system that may no longer exist, around a star that may have died billions of years ago. The scientific questions surrounding 3I/Atlas are profound. Its extreme velocity suggests a long and violent history. To reach such speeds, the comet must have experienced multiple gravitational encounters, slingshot after slingshot around stars, and perhaps even stellar remnants, accumulating velocity over billions of years. Each of these encounters would have altered its trajectory, sending it careening through the galaxy on paths that are essentially impossible to trace backward beyond a certain point. We can constrain where 3I/Atlas came from in a statistical sense, identifying the general population of stars whose kinematics match its velocity, but pinpointing an exact parent system is almost certainly beyond our capabilities. The chemical composition offers clues about formation conditions. The dominance of carbon dioxide over water suggests that 3I/Atlas may have formed in the outer reaches of its parent system, beyond the water ice line, but within the carbon dioxide ice line. Alternatively, it may have formed closer in and been extensively processed by radiation during its interstellar wanderings. The absence of detectable iron in an otherwise nickel-rich environment is puzzling and may point to unique formation or evolutionary processes that don't occur in our solar system. The reddish spectral slope reported by some observers indicates an organic-rich surface consistent with the complex carbon chemistry seen in many primitive solar system bodies, but possibly modified by cosmic ray bombardment over inconceivable timescales. The structure of the comet itself remains poorly understood. The wide range of possible nucleus sizes, from a few hundred meters to several kilometers, reflects the difficulty of separating the central body from its surrounding coma. Some estimates suggest 3I/Atlas could be the largest interstellar object ever observed, with a mass potentially exceeding 33 billion tons. If true, it would dwarf both Oumuamua and Borisov by orders of magnitude. But these numbers remain uncertain, and the true size may not be known until the comet fades and the coma dissipates, if even then. Perhaps the most profound aspect of 3I/Atlas is what it represents for the future of astronomy. This discovery was not an accident. It was the result of deliberate investment in wide-field survey telescopes designed to scan the entire sky repeatedly. The Atlas system was built for planetary defense, but its capabilities extend far beyond spotting potentially hazardous asteroids. The Vera C. Rubin Observatory, currently beginning operations in Chile, will dramatically increase our ability to detect faint, fast-moving objects. Astronomers predict that the era of interstellar object discovery is just beginning. Instead of one such visitor every few years, we may soon be detecting them monthly or even more frequently. This prospect has inspired ambitious thinking about how to study these cosmic messengers more closely. ESA is preparing the Comet Interceptor mission, scheduled to launch in 2029. Unlike traditional space missions that target known objects, Comet Interceptor will park in a gravitationally stable point near Earth and wait. When a suitable target is discovered, whether a pristine comet from the distant Oort cloud or, most excitingly, an interstellar object, the spacecraft will be dispatched to intercept it. A close flyby, or even an impact designed to kick up material for analysis, would provide information impossible to obtain from remote observation. The odds of catching an interstellar object suitable for Comet Interceptor may be low, but the mere existence of such a mission shows how seriously the scientific community takes these opportunities. Other proposals go even further. Some researchers have suggested that rapid response missions could be launched to intercept interstellar objects with relatively short notice if detection systems improve enough. Advanced propulsion concepts, including solar sails and even laser-pushed light sails, might eventually allow spacecraft to catch up with these fast-moving targets. The Breakthrough Starshot Initiative, which aims to send tiny probes to neighboring star systems using powerful ground-based lasers, could potentially be adapted to chase down interstellar visitors. We might not need to travel to other stars to study material from other planetary systems. The galaxy, it turns out, is delivering samples directly to our doorstep. The philosophical implications are equally profound. Every rock, every ice ball, every speck of dust in our solar system shares a common origin in the cloud of gas that collapsed to form the Sunday, April 6th billion years ago. We're made of the same stuff as Mars, as Jupiter, as the most distant comets in the Oort cloud. But interstellar objects are genuinely foreign. They carry material that formed under different conditions, around different stars, perhaps in galactic environments vastly different from our own. Studying them is like receiving messages from alternate realities, glimpses of how nature builds planetary systems when the initial conditions vary. The diversity already evident among the 3 known interstellar objects supports this view. Oumuamua was bizarre and asteroidal, showing no cometary activity and exhibiting unexplained acceleration. Borisov was reassuringly comet-like, chemically similar to what we see in our own solar system. 3I/Atlas is something in between, a comet with familiar behavior but unusual chemistry and an ancient pedigree that connects it to the early history of the galaxy. If 3 objects can be this different, what will the 4th bring? The 5th? The 100th? As our detection capabilities improve, We will build up a statistical picture of what the galaxy produces, learning how common or rare our solar system's particular mix of ingredients truly is. As December 2025 unfolds, 3I/Atlas is emerging from the solar glare, once again visible to ground-based telescopes. By mid-December, it will be far enough from the Sun to be observable at midnight. On December 11th, it will pass within 2 degrees of the half-illuminated Moon, offering a celestial spectacle for anyone with a decent telescope and dark skies. December 19th marks the comet's closest approach to Earth, still impossibly far at 170 million miles, but closer than it has ever been or ever will be again. Opposition, when the comet is up all night, won't occur until late January 2026, by which time it will be considerably fainter but still within reach of large instruments. The observations will continue as long as they remain scientifically valuable. Astronomers will track the comet as it recedes, monitoring how its activity declines as solar heating diminishes. Eventually, the coma will fade, and the nucleus will once again become a cold, dormant body, indistinguishable from countless other small objects except for the trajectory that marks it as interstellar. 3I/Atlas will continue outward, passing closest to Jupiter in March 2026 before leaving the planetary region of the solar system entirely. It will take millennia to reach the outer fringes of the Sun's gravitational influence, and longer still to reach the next star along its path. Where it will go, what it will encounter, whether it will ever again pass through a planetary system, these are questions that can never be answered. But the knowledge gained during this brief encounter will persist. The data now being collected represents a time capsule from the ancient galaxy, frozen evidence of processes that shaped worlds we will never see. Every spectrum tells a story about chemistry. Every image constrains structure. Every measurement of trajectory and velocity speaks to dynamics spanning billions of years and hundreds of light years. In the grand sweep of cosmic history, 3I/Atlas is just a mote of dust on an endless journey. But for those of us watching from this small rocky planet, it is a window into the universe's past and a herald of discoveries yet to come. The story of interstellar objects is just beginning. Oumuamua taught us that they exist and can be profoundly strange. Borisov showed us they can be familiar. Now, 3I/Atlas has demonstrated that they can be ancient beyond comprehension, travelers from eras when the galaxy itself was young. Each new discovery adds to our understanding, challenges our assumptions, and expands the boundaries of what we know. The universe is not empty. It is filled with wanderers, billions of them, crossing the vast distances between stars, occasionally passing through systems like ours, carrying secrets from places we have never been. And we are finally learning to see them,